Hello, everyone. Welcome. I'm Arpad K. I'm going to be taking you through reversible debugging with RR, which sounds magical, and we're slowly going to make it less and less magical. But to begin with, what is RR? Fundamentally, it's still a debugger, just like all the ones that you're aware of. The user interface is essentially the same, so if you're familiar with those, you'll feel right at home here. But like literally none of us use debuggers, let's be honest. So I did a little like fake social science experiment here. We've got our fake data. This is the population of all computer scientists. And of course, this is the print debuggers, 99% overwhelming majority. And then we have the clinically insane up there, 1% who actually use these debuggers. And that's, of course, that's us. And so, yeah, that 1% that actually uses debuggers, they use it either in your terminal or in your IDE if you're built that way. And here are some places where you might be able to use RR. No comment. And it does time travel, which is sort of the main selling point. What does that mean, though? What is that? I sort of thought it would be fun to take you through from first principles what the design of RR is, to try and invent it together, because I think one of the main symptoms in computer science right now is we have a lack of creativity. We're so used to the assumptions that are around us all the time. I think it's fun to try and break that. So I'm going to sort of start from nothing, and we're going to try and invent RR from scratch. So just imagine, you're an alien guy from an alien planet in your flying saucer, and you don't know what a debugger is. You have no idea what this is all about, but you're writing your alien programs, and you have a bug, which, of course, you're running your program, and your flying saucer crashes, as it has been known to do. So what do you want to ask your alien computer to try and figure out the cause of this bug? Right, you had some assumption about what your program was going to do, and then that was broken, and then you want to figure out what. And I genuinely want you to think about that. If you're watching the recording, I encourage you to pause every once in a while and maybe see if you can figure out the next component of this talk, because it's a good exercise in creativity. So let's get more specific to help you, discuss what we're talking about. So you have some alien code here. You have some code that gets some pointers, some data, very useful, and then you have a lot of code in the middle that I've just elided out. It doesn't matter. You don't know what it is. It's like a big mess. Maybe your alien pal wrote it, or you a week ago, so it's just illegible. You have no idea what's going on in there. And then at the bottom, you want to actually use what you got, but it turns out that it's null. So your alien computer sort of whips you to that line and says, hey man, there's a seg fault. I don't know what to do. Zbop is null. What do you want me to do? And again, genuinely, I want you to ask, what's the question you want to ask here? What do you want to know about? And go for the obvious. Try and think about what would be a useful thing to know here. So let's see. Usually when you debug something like this, you do this sort of process where you add in a bunch of print statements, try and follow the lines from the start to finish. So you would put in a print statement after to say, oh, Zbob is fine, and then put a couple print statements. If we go here, it turns out the value is like this, and then we come back, it's like that. Or if you use a normal debugger, you do essentially the same thing, except instead of putting print statements, you look at the values automatically. Not much better, if you ask me. So if you're doing this process, this ancient but very cool looking process, that's clearly going to get you nowhere. I mean, how are you ever going to debug this following these wires around? But this is essentially what best practice is in software engineering. I think this is on its face kind of crazy. I would hate to be this person. If this was programming, I would give up today. I would end programming. So you're just in this loop of asking, what happens next? What comes after this line? What value does this take next? So you're going from cause to effect. From cause to effect. Is that a good idea? Is that the problem that we were faced with? When you saw this crash, was your question cause to effect? Was it? It's the only thing that debuggers or printf let you ask. It's that one direction, but as you keep asking this, you're not getting that far. You're following these piles of wires, and if you have a big enough program, you're screwed. You have no idea what's going on. What if this is a bad idea, what if we do the opposite? What if we flip this arrow and we go from effect to cause? So instead of asking what happens next, we're going to keep asking what just happened? What happened to get me here? And instead of asking and then what, we're going to ask why, what was the change? This seems a little sci-fi crazy, but let's see if we could make it happen. So how are we going to build something that lets us go from effect back to cause. How is this going to work? So again, genuinely, if you want to experiment with your creativity, try and think about what you might do to have a program and be able to go backwards from effects back to causes. So the problem is we need to build something that executes codes backwards, but like you can't really do that. Like if you have just a pile of instructions, you can't just replace them with like an anti-instruction and then run that and then it like undoes the program. You can't really do that, even for trivial things like add or jump, because they overwrite their registers. Even though they're deterministic, there's no like inverse for every possible instruction. You can't just invert a program. You need to be a little smarter about this. So how do we run code backwards? Let's go for the like trivialist, simplest idea that you might ever get, which might actually be the first idea of programming ever, because like Ada Lovelace did this. You just record the state of your program at every instruction. You just write it down. You stop, you just write out the entire memory, all the variables. You just make a big table like she did here. She's got a lot going on in this 25 instruction program. But this would work. Like you can now jump back and forth, run code backwards and forwards because you just read off what the values were. Yeah, that's an idea. I mean, it totally would work. And again, it might be the first idea in programming. Like literally right after they made the first program, they were like, let's do this. But it's not amazing. It's too much space. You probably have like, I don't know, 8, 16, 32, 256, a terabyte of RAM, depending on what kind of person you are. We can't just, after every instruction, just write that out to disk. You're screwed if you do that. So maybe we can be a little smarter. Like only record the changes that actually happen. Most instructions barely do anything. They just change like a register and move on. And actually, Ada Lovelace also had this idea. You can see all these dots she's got going on. That means like the value in there didn't change. She didn't bother to keep writing it down. It's the same value as it was before. And even better, she's got empty spaces where the variables aren't live, like they're just whatever is in there. We haven't used them yet, or they're not relevant right now. She only records the changes that actually happen, right? So that saves you a lot of time and effort. But in a modern computer, that's still horrible. I mean, it takes too long to do it, but then to go in reverse is like way worse than before, because let's say I'm down here at like instruction 20 or 18, and I want to go up like 3 instructions. I only have the changes, like we only wrote down the changes from the start. So I have to just go from the start every time, which kind of sucks. You may as well just run GDB again. Okay, so maybe we can do a little bit better. We need to exploit some knowledge from our animation friends or video editing friends. You might have heard of like keyframes in Flash or Premiere Pro or something, where you have these stages where everything is recorded and then between them things are interpolated. And we can do the same thing. We can like have keyframes where we record everything and then in between them we go back to the way that we did it with the changes. And that's a good idea. That like kind of works. So people do this. This is a thing that actually does happen. But it's still too much space and still too slow to record changes because you want to be able to run this on any program. I mean like Firefox, whatever, right? That'll still be too slow. This does kind of work. So if you have GDB on your machine, which you do, that does this. But it's not good enough. We can do better. So fun fact, we live in a causal universe. So here's Minkowski talking about the causal universe. Doesn't really matter, but that's pretty useful. We don't live in a deterministic universe, but the hardware engineers, which are all smarter than you, computer scientists, it's true. They made CPUs that are like overall pretty much deterministic, which is like amazing. You guys should probably like thank whoever you pray to that they manage that, because that's crazy. But they are largely deterministic. So like the same add instruction, same inputs, every time it'll give the same result, which you should appreciate. We can together make use of these 2 facts about the universe and people smarter than us to say like, why am I recording all this stuff if it's going to happen the same anyway? Like, why am I recording that add 3, 2 is 5? That is a big waste of my time. So let's not do that. Let's only record at times where we have these non-deterministic things. So your computer just have some, non-deterministic parts, such as you, and like the internet or whatever, which is other U's. At these points, we can record all of those state bits that we want to record. Between them, we just do nothing. It's all deterministic. We rely on the computer to run the same way that it did the first time. Okay, that's interesting. That actually fully works. We can run code in reverse on like serious code bases, non-trivial things. And so how does that sort of work? Here's some assembly code that no one should bother to read. It's from Quake. But like, let's say we're down here at this instruction. We want to say like, what is going on in this crazy subroutine? And we want to go back to the first time we loaded the famous coefficient that you might be aware of from Quake. We want to go back there. What does our debugger do? So we have some of these keyframes. That's not how it would look in the real world. It would be like tens of thousands of instructions, probably more, between keyframes. But what it would do is it doesn't generally have an idea, given an instruction, what keyframe it is in. It's not always the case, but generally the case. So it would go backwards from your current instruction. So it would say, what's the latest keyframe? I'm going to run forward and see if I hit the instruction this guy cares about. If not, I'm going to go to keyframe 2 and start running down again. And I'm going to go to keyframe 3, and it's actually going to hit it this time. And now it has essentially run your program in reverse on a computer that can only run forward. And that like totally entirely works. So enough dilly-dally. Let's actually see this work. I didn't have enough time to like open my terminal before this. So we're going to do that live. We're going to open up Emacs. I'm going to show you a program that's pretty much exactly what we looked at. So let's look at the presentation file. I have this null program, which is basically exactly what we had, but with like actual types. Probably no one bothered to read this code. It's essentially the same that we had with our alien flying saucer situation. And so we have this like pile of code in the middle where something happens. We're going to assume we don't know that code. We're going to see how this works in RR. And it's going to be super painless. So if I open up a terminal here, let's do this. I'm going to compile this code normally. And that is actually a fairly important statement to make. RR doesn't require you to do anything special with your code. It doesn't put anything into your code. We can just instrument any binary. So if we just compile in debug mode, C++23 on this program, that compiles, and no special flags. RR is not mentioned. And if I run this code, it's going to crash. OK, fair enough. It crashes. Now, I'm going to run this under RR using nothing but putting RR record right behind that line. Like that is the only thing you need to do after you go home after this and you pull out your laptop. You can just run your code under RR by doing this. So if I just do RR record a.out, I get a sec fault. Almost nothing changed, but RR said, OK, I'm going to save what you did. I'm going to record everything that happens in this file, and we can go ahead and work from there. And then if I open up GDB in my editor here, and I say RR replay, which you can do in the terminal, I will get a normal debugger. And if I continue, I'm going to go to the line where we get the sec fault. So we can see in the top left, it says, hey, you got a segmentation fault. That pointer is null. I crashed. Do something about it. And we can have a look. Like if I print v, it actually is just straight up null. And the question now is, you're that alien in the spaceship. I see the effect. What is the cause? And let's demonstrate RR working in the real world. I don't know if you guys are aware of watch points, but they essentially stop the program anytime a value changes. So I'm going to say, hey, watch the value of v. And I'm going to run the program backwards from where I am to see who was the last person that modified that pointer. Someone set it to null. Someone deleted this stuff. I need to see who it is. And this is a huge pile of code. This will just find it for me automatically. So you might be familiar in GDB with commands like next. You click the step button and it does like the next instruction. In RR, there's also reverse next. You might be familiar with continue, which is like the play button. There's reverse continue, which does the same thing, but goes backwards. So now if I type RC for reverse continue, you could type it out as well. We reverse continue back. It's going to whip me straight to the line where the pointer was set to null. And I don't have to do anything. I don't have to know anything about the program. It could be someone else's code across the world. RR would find it. And we could see, OK, well, it's in some nuke data instruction. But like, what was going on? Why are we in nuke data? Like, that's not that helpful. I don't want to nuke the data. OK, we can do even better. You might be familiar with the finish instruction, which just runs the function you're in to the end in GDB. It's like run to cursor in VS Code. We can do the same thing, but again, just put reverse in front of it. So if I click reverse finish, or RF, it's going to go back to the call site of this function, and it says, hey, if you pass me less than 2 arguments, I'm going to nuke the data, right? And that is the bug, okay? That is fundamentally what is wrong with your flying saucer. And so that is how you use RR in the real world. Why should you use RR? So let's have a look. There's some user interface improvements into being able to go back. I'm sure you've all used debuggers and been like, oh, I stepped over the line that I'm interested in, and I have to do the whole thing again. I have to like rerun the debugger, and I'm just like annoyed and bothered, and then you just start putting printfs in. You don't have to do that in RR. You just like, oh, I went over the line. Let me just put reverse next. Or like in VS Code, just click the back button. OK, that's fine. Another amazing feature, which would be amazing on its own, is that you get these traces that you can just like send to anyone to debug. So if you're working on a team and you have like a unit testing CI thing, and like a Heisenbug shows up that only happens in like 0.1% of cases, and you've managed to reproduce it, but you don't have it under the debugger, you don't have the logs you wanted, you're screwed. You may as well have not reproduced the bug. If you have it running under RR, you will always have like this full trace of your program that you can debug. I think this is like a game changer on its own. And as we discussed, like this is what debugging should be. Debugging isn't going from causes to effects where you're trying to put in breakpoints to guess what went wrong. You have an effect, you have a bug, and you want to find the cause. This is what RR lets you do. How do you use RR? You go to this website, and it's like 2 commands to set it up. And then to use it, you just put RR record before your executable. So that's nice. Only on Linux, though. So, you know, that's a limitation if you don't have Linux, but you probably have WSL. So that's fine. You need a fairly modern CPU. Sorry, ask Intel and AMD. But like, if you have a fairly recent computer, you're fine. And actually, some ARM chips run it as well. So like Apple M1 and further, Neoverse chips and further. And if you have a multi-threaded program, it'll run under RR. It'll just be made sequential. So you cannot, unfortunately, you cannot debug parallel bugs. So it's not a cure-all, but for every other kind of bug that isn't like parallelism related, this is amazing. But you know, maybe you're not satisfied. Like maybe you want to see, maybe I can make debuggers even better. And there is next steps. So there's this idea called omniscient debugging, which is like, I think, even cooler than time travel debugging, but it's really not that much different. It's essentially the same thing of recording and replaying this trace. But one thing you can't do in RR is ask questions across time. Even though it kind of feels like you can do that, it's not really. You're only at one point in the program at any one time. With omniscient debugging, the point is that you can ask questions of, like, give me all the times this variable was changed to this value, and then tell me why it was changed at that value. And it'll do all of that in one go. And there's people working on this. So here's Pronosco, which is based entirely on RR. And it's actually a pretty funny story. I think the developers on RR realized they were making something too cool to be like free. So they just like forked RR, and they're like, this is the good one. And then that's the open source one, which is just like GDB. But this is like crazy cool. It is RR underneath, but it has this like understanding above it where you can query more complicated stuff about your program. So if you want to work on something that will actually make the world of programmers a better place, probably help out on this. And yeah, thank you so much for listening.